Okay, so last time I explained this triple cross product, and I wrote that this vector is given as a linear combination of these things, and in the final statement, instead of writing this, I wrote this. Okay, so in your notes, just correct that. We don't have this, we have this. So these three red vectors lie in the same plane because they are all perpendicular to the same vector r cross q. Okay. Okay, so that's the correction. Now let's do one more property of. Okay, so one last property of cross product. We have P cross R. This is given as P R times sine theta. Okay, so theta is this angle, which I'm now using here. Okay, so how do you prove such a thing? Okay, you see that we are talking about lengths of some vectors. Length of a vector is always square root something. So the easiest way is square both sides. So square of the length of this vector, is it equal to square of this length times square of this length times sine square? Okay, now what you do is you know the coordinates of this, calculate patiently the square of the length, keep it somewhere, and then calculate this side, multiplying. Okay. Observe that you have sine square here. Okay, so at one point you will have 1 minus sine square or something, so that will give you cosine square, which you are trying to find, because on this side you will have a cosine square, okay, length of something. Why do you get cosine square? Because the square of the length of a vector is the dot product of the vector by itself. When you take the dot product, you get cosine there. So on this side, you will have cosine square. On this side, you have sine square, but at some point, you will have 1 minus sine square. Simplify everything and then check. Those two expressions will be the same. So that's the easiest way to see that this side is equal to this side. So what is the meaning of this? Okay, so this part, so this gives the area of something, okay? This gives the area of, okay, so what do we get? We get, this is P, this is P cross R. Okay, so let me change these things. Let me make this again according to this. So we have Q cross R. And Q, and here I have R. Okay, so as this thing. This gives the area of the parallelogram formed by Q and R. Okay, because sine theta here will give you this height. Okay, you are multiplying it with this length, you'll get this area. Okay, so let's now look at the other section. We've now passed to lines and planes. Okay, so our next topic is to review from high school is lines, planes, and curves in most simplest terms. Okay, so we are interested in equations and algebraic equations of the lines and planes, and also vector equations, because sometimes one of them is very convenient in calculations, sometimes the other. One of them carries one information, the other carries another information. they obviously, if you have an equation, parametric or analytic equation for a plane, it's always the same plane, but to read what is said, what information you want about the plane is different from both of them. Some of them are easier to read. So let me show you what I mean. So in the plane, okay, equation of a line is something like this: ax plus by plus c equals 0, where a, b, c are constants. Okay. We also want some parametric equations. Okay. So for this thing, we need some information. Okay, so the line passes information needed for parametric equations. Okay, first the line passes through a given point, say through P sub 0, a point. Okay, so there is a point P sub 0. Sometimes we see this as a point, sometimes we see it as a vector. Okay, so P sub 0, let me write like this. Since we are in parametric equations, we will consider vectors. Now we look at this point and we see it as a vector. And the direction. The line is parallel to some vector, let's say P1. Okay, so P1 is, say, some vector here, P1, and it is this vector. You see that all vectors start from the origin. So our line is something like this. This is our line. Okay, so this is our line. Okay, so this is our line at. It passes through this point and parallel to this line, so this information totally defines this line. How do we express this? An arbitrary point on this line and arbitrary point on this line is denoted by, let's say, since I call this L, let me denote this by LT. Okay, so here LT is equal to, okay, so parametric equation is a way of describing a location. You just give an address. Go to this direction, turn right, and follow this direction. Okay, so that's what we are going. So you use the only information available to you. Go to this point and follow the direction of this line. Okay, so that's your address. So first go to P sub 0. Okay, now let me put a vector sign here. And then in the direction of P1, continue in the direction of P1, and you can go as many direction as many distance as you like. Okay, so this is the equation, parametric equation of this line. Now you see that when you write it this way, that we are working in 2 dimensions disappears. Okay, you can give this description in any dimension. There is a point in Rn. Well, in our case, it will be only R2 or R3. There is a point in space, and there is a direction, also another point. Okay, so first go to this point, then follow the direction of the other vector, and the expression will be given like this. Okay, so this is, so note that this description works in any dimension. In particular, we are interested in R3. In R3. Okay. Generally, we write these equations for R3. When we want to work in R2, we just drop the last coordinate. Okay, so in R3, let me write this equation. So if, say, P0 is equal to, again, let me use my favorite point, and P1 is 4, 5, 6. Okay, parametric equations of the line passing through P0 in the direction of P1 is given as follows: LT. First I go to P sub 0. Now I'm deliberately writing the same expression to show you that nothing changes. Okay, so now I can work out the numbers. 1, 2, 3 plus T, 4, 5, 6. So this is equal to 1 plus 4T, 2 plus 5T, 3 plus 6T, and you have to remind yourself that T is your free parameter. Okay, depending on the value of T, you are describing a different point on the line. Okay, so this is my x coordinate. Okay, so let's use this one. So this is my x coordinate, this is my y coordinate, and this is my z coordinate. So we can also write this as follows. Write this as follows. X. Okay, in this case, I don't write x equals 1 plus 4t because x depends on t, and I want to remind myself that x is changing as t changes. So I write x of t. Okay, so this tells me that x is a function of t, which it is, 1 plus 4t, and y of t is equal to 2 plus 5t, z of t is equal to 3 plus 6t, and of course I have to tell myself that t is the real parameter. Okay, so these are called either this one or this one. These are called parametric equations for the line, and of course now the other thing is in the plane. I can give a line by just one equation. In the space, in 3 space, you cannot give a line by one single equation. Okay? One single equation means that, generally speaking, you have 3 variables x, y, z. You bind them in one equation. Most of the time, it means that one of them can be found if you find the other 2. So this one always depends on the other 2. So you have only 2 free variables. So 2 free variables means that we are talking about a 2-dimensional object. We will be interested only in linear equations. So if you have one linear equation like this one in x, y, and also z, then one of them can be solved by the other. So you have only 2 free variables. They are linear. So you are talking about a plane. In the plane, if you give one equation, dimension drops by 1 and you get a line. In 3 space, you get a linear equation, dimension drops by 1 and you get a plane. So you don't get a line. In order to get a line, you have to give the equation of another plane, and when these 2 planes intersect, they give you a line, and that will be your equation. And then that we can derive from here. That will be by eliminating the parameter t. Okay, so let's look at that. This time, so from x equals, now I'll write an expression in x. I'll eliminate t, so I'm using x here. So these are just for personal taste. Okay, so I can eliminate t from here. T is equal to x minus 1 over 4. From the other one, y is equal to 2 plus 5t t, t here is equal to y minus 2 over 5, and z is equal to 3 plus 6t, so t here is equal to z minus 3 over 6. Okay, they are all equal to each other because they are all equal to t. So I have here x minus 1 over 4 equals y minus 2 over 5. This is equal to z minus 3 over 6. Okay, so in R3, these define a line. Okay, so if you take any two equations here, for example, okay, so for example, I can take this equation defines a plane. Let's say, let's give a name capital P1, okay, in R3. So take this, for example. So these also define a plane. Let's say capital P2 in R3. The line we are interested in is the intersection of these two planes. Okay, so let's combine this. Our line is the intersection P1 intersect P2 of these planes. Okay, so these are called symmetric equations. You have to know these names because somewhere you say, okay, find the symmetric equations of this line. You should know where to look, or if it's an exam, you have to know what to do. Okay, so these are called the symmetric equations of the line. Okay. So here you see that when we look at these symmetric equations, sometimes a symmetric equation will be given. We read an information from this. The line passes through this point, 1, 2, 3. Okay, you see that that's true. When t is equal to 0, this point is on the line. Okay, so that information, you can read that information from here. And in the symmetric equations, it is given here, 1, 2, 3. And this line is parallel to this vector. We know from the parametric equations. This is here. And we read that information also here. This line is parallel to the vector given here. Okay, so the question is, what if one of these entries was 0? If that entry is 0, so suppose instead of 5 we had 0, okay, here. If instead of 5 we had 0, then we don't have t here, so you don't attempt to eliminate t. So this is just a different equation, y equals 2. Okay, so this equation does not appear. If the direction that the line is parallel has a 0 in one of its coordinates, then that equation does not appear, but you have instead something like this. So let me give an example and also draw a picture, because in some cases it is easy to draw a picture, so we show off by drawing three-dimensional looking pictures. Okay, so let me say this one. From the symmetric equation, we immediately read C, a point lying on the plane, on the line. Okay, this is a line on the line and its direction. Okay, so x minus a over, say, alpha equals y minus b over beta and z minus c over gamma. When you write alpha, beta, gamma, it looks more scientific. So let's do it that way. So here the line passes through the point A, B, C and is parallel to alpha, beta, gamma when alpha times beta times gamma is different than 0. So this means none of them is 0. So if one of them is 0, okay, so if the line is parallel to, say, 0, beta, gamma, then the symmetric equations become, as I explained over there, when alpha is 0, for example, x equals a plus alpha times t, but alpha is 0, so you don't bother eliminating t there. So this becomes x equals a, and then y minus b over beta equals z minus c over gamma when beta times gamma is different than 0. Okay, so if one of them is 0 again, then you have y equals b. Okay, so in this case, for example, in this last case, the line lies in the plane x equals a. Okay, because no matter what y and z coordinates are, you will solve y and z from these equations. X is always a. So when you draw this, okay, so here we can draw it. This is x, this is y, this is z. And at x equals a, here we have a plane. So let me again draw the plane like this. Okay, so it also goes like this. So we have this plane. So this is the x equals a plane. Okay, so this line lies there, and our line will be something like this. Any point on this has x coordinate a, and it has some y and z coordinates. Okay, so this is the kind of information you read from the equation of a line. Either you have vector equations or symmetric equations. Okay, let's come to equation of a plane. So this will be more important for us because we will be looking at tangent planes later on when we come to integration and other things. So let's see. Okay, so equation of a plane. Okay, so now next equation of a plane. Okay, of course we are interested in R3. Okay, general equation is of the following form. Ax plus by plus cz equals d, where a, b, c, d are numbers. These are real numbers. Okay, so as I explained before, you see that this defines you a two-dimensional space, because if c is different than 0, for example, I can say that c is equal to, take everything to the other side, divide by c. So z is equal to an expression, a linear expression in x and y. So this defines a two-dimensional plane. One equation drops the dimension by 1 in general. Okay, so it is in this case. Okay, so we want to see this geometrically. If you want to write parametric equations for this, okay, you have to choose a point on the plane. First, you go to the point. Now, there are many directions to go. In the line, there was only one direction, so you said follow this direction. But for the plane, you have all these infinitely many directions. So what you do is generally you consider two vectors that lie in the plane, but all vectors are at the origin. So you take two vectors which form a plane passing through the origin, and our plane is parallel to that plane. And then you give your directions according to these planes. You say you have two choices. Okay, mathematically you have two parameters. Okay, you can go along this vector as many times you like, and then follow the direction of the other. Okay, so this is a real address. So let us first look at that one. So parametric equations. Okay, so the plane passes through P0 and is parallel to the plane formed by the vectors P1 and P2. Okay, so this information now totally defines the plane parametrically. So our picture is something like this. Okay, so P0 is a point here, and say P1 is a vector like this, and P2 is a vector like this. They form a plane here at the origin. Our plane is going to be parallel to this. So we describe an arbitrary point on the plane. Okay, so describe an arbitrary point on this plane. This means give parametric equations using P0, P1, P2. Okay, so an arbitrary point on this plane is going to depend on two parameters because we have two directions to follow. First, you go to the vector P0. Okay, so first you go here. Now you can follow P1 by a length of by the parameter s. Okay, and then when you stop, you can now change your direction and go in this direction. Here, s and t are real numbers. Okay, so sometimes this is useful, but you see it is how do I go from here to here is complicated. Okay, in the line case, the plane is easy. We can pass from any equation to any other equation. When it is a line, even in R3, it is easy. But here, this information is a little bit complicated. So we try to find another information about this plane, which is easier to follow. And that information is again derived from this thing. If we have two vectors, they form a plane. Okay, this plane can be described by one vector also. If you take the cross product of these things, you obtain a vector perpendicular to this. So instead of giving the parametric equations, we say write an expression for the plane which passes through P0 and is perpendicular to this given vector, P1 cross P2 in our case. Okay, so that part is easier because any vector in this plane is going to be perpendicular to this line, and we have an easy way, an algebraically easy way of describing perpendicular lines. We take their dot product, the dot product will be 0. Any point, any vector in the plane is going to be perpendicular to this direction that I give. So their dot product will be 0. So that gives us an easy expression for the plane. Okay. So, an easier way to describe a plane is to give a point where it passes, or well, let's say a point on it, a point on the plane, and the direction, and a direction perpendicular to the plane. Okay, in the previous example, the plane passes through P0 and is perpendicular to P1 cross P2. P1 cross P2. Okay, so let us call this N. Normally we call if a vector is perpendicular to an object we are interested in, we call it the normal vector. So in this case, we are interested in this plane. This vector is perpendicular to the plane. So technically, it's called the normal vector, a normal vector to the plane. We say a normal vector because if you multiply this vector by 5, it's still perpendicular. Okay, so now we can express this easily using dot product. Okay, so remember that two vectors are perpendicular to each other if and only if their dot product is equal to 0. Okay, so we have a vector which is going to be one of those vectors. So what is the other vector? Okay. Okay, so we have a point okay, so x, y, z. So we have a point here, p sub 0. Okay, so its coordinates are, okay, so let me give some numbers here, say a, b, c. Okay, an arbitrary point on the plane, the plane is going to be something like this. And this is an arbitrary point on the plane. We don't know its coordinates, so they are unknown, x, y, z. Okay? And we have a direction here. Okay, so if I take p cross, so it is going to be something like this. And let's say this one, and this is orthogonal to the plane. Okay, so maybe it is like this. It goes and intersects the plane here, and it is perpendicular there. Okay, so we have to find an arbitrary vector on the plane. Okay, so this vector, if you consider this vector is not on the plane, but if you consider this vector, okay, so this difference, okay, so let us call this P an arbitrary vector, arbitrary point on the plane. So this is P minus Q, P minus P sub 0. Okay, obviously, when you are doing it algebraically, P minus P sub 0 is here. Okay, and I want them to be perpendicular. Okay, so now I have an equation. Geometrically, when I draw this, I know that the vector will lie here, but that's the position. I am interested in its direction. When I'm doing calculations, I must remember that all the vectors are here. I want this vector to be perpendicular to this vector. So, okay, here I take the dot product of this with this. Okay, so these vectors are going to be perpendicular. Okay, so for the point P to be on this line, on this plane, we must have Okay, so P minus P sub 0 is this vector. I dot product it with n, and this is perpendicular, so this is 0. Okay, so let us write this in that form. Okay, so I'll erase this. Okay, so let n be the vector A, B, C. Okay. Then we have P equals X, Y, Z, and P0 equals A, B, small c. Okay. Now I write this. So from here I write P minus P sub 0 dot n equals 0. This gives me, okay, P dot n, this times this. I have A x plus B y plus C z equals, I'll take this minus to the other side, this times this. So here I have a number, A plus B plus C. Okay, so we call this D. Okay, so when we have an equation like this, okay, so this tells us the following. An equation of a plane is of the form ax plus by plus cz is d. Here a, b, c is orthogonal to the plane. Okay, so how do I interpret this one now? Okay, so it is this product. It is a dot product of this particular point I choose on the plane. But how did I choose P sub 0? Which condition I put on P sub 0? The only condition I put on P sub 0 is that it lies on the plane. Okay, I can choose any other point on the plane, and this dot product is always going to be the same number. Okay, miracle. Okay, so call this. Okay, so here and A, B, C dot product P sub 0 for any P sub 0 on the plane. Okay, let me emphasize that that's a point now. For any point P sub 0 on the plane is fixed, is a fixed number, is the same number, to make it sound more spectacular. Okay, so once you know the normal to the plane, and then you take the dot product of that normal with any point on the plane, you will always get the same number. Okay, so that's what this tells us. So in order to write the equation of a plane, then we need two information. You need a direction which is orthogonal to the plane, and you want a point on the plane. Okay, so how do we use this information, for example, to write the equation of a plane passing through 3 points? Okay, so since elementary school, we are told that 3 points determine a plane, and here we have some high-tech tool which tells us that we can write equations of this. And let us check if we can write the equation of a plane passing through 3 points. How to use this technique to write the equation of a plane passing through 3 points 3 points in space. Okay, so before we panic, because you see, given 3 points in space, it doesn't fit any of this description. We say our technique says that we want a point on the plane. Okay, we have 3 of them. We will choose one of them. And then the next information is we want to find a direction perpendicular to the plane. Well, since we have extra 2 points there, those extra 2 points must give us a direction perpendicular to the plane, because we know that they define a plane. If there is a plane, there is an orthogonal direction. Okay, so we should be able to do that. So what we do is we fix one of these points and we join it to the other 2 points. Then you get 2 vectors. Okay, those vectors are, when you write them algebraically, they are actually at the origin. You take their cross product, you get something perpendicular to them. Okay, so that is your ABC, this big ABC. Okay, so suppose we have the point P0. Okay, since I said 3, so let us write P1, P2, P3 are the given points. Okay, so take P2 minus P1, P3 minus P1 as 2 vectors lying on the plane. Okay, their cross product is orthogonal to the plane. Okay, now we have all the information. Okay, now we have enough information to write the equation of this plane. Okay, so what is the equation? Okay, it's the equation is this one. We take okay, so we take P2 minus P1 cross P3 minus P1. Okay, so this is our normal vector. We dot product it. Okay, so let's read it. This part is easier. We dot product it with x, y, z. Okay, so we dot product it with x, y, z. This is equal to, let's read this side. We take the same vector. Okay, so let me write it like this. So we take the same vector, P2 minus P1 cross P3 minus P1. We dot product it. Okay, what is this small ABC? This is any point on the curve. Okay, so let us take any of these things. Okay, just to make this thing look symmetric, I can write P1 here. I can write P2 here, P5 here, whatever. Choose any point on the plane. On this side, you'll get a fixed number. That is assured from here. When you look at it this way, it is clear. Okay, but when you look at it here, it looks like a miracle that whatever point I put here, I'll get the same thing. Okay, why does it sound miracle? Because when I say whatever point I choose, I'm exaggerating. I cannot choose an arbitrary point here. I can only choose points on this plane. Okay, every point on this plane will dot product to the same number with this given normal. Okay, so this is the equation of a plane passing through these 3 points. So, okay, maybe we can do one more thing. Let me check if we have missed something. Okay, then. Okay, let's stop here for today. So next week I'll look at surfaces and curves.